Hello, today we'll be doing the multiple fin problem. So I'm just going to jump straight into it. So right here, these are all the givens: the ambient air, heat transfer coefficient, the thickness of each of these fins. LF is the length of the fin. LB is the length of the base, basically a solid material, all right here. Right here is two different materials, so there's a contact resistance between them, a thermal contact resistance, and then on the top we have the temperature of the chip. This example, of course, is the computer chip with multiple fins, and then you have width and length for the area. And right here you have a thermal conductivity for this material. So part A will be asking for thermal resistance network. Part B will ask for the efficiency of a single fin. Part C will ask for the efficiency of the overall fins. Part D will ask for the heat rate. So let's just jump straight into it. So starting off on the top, we have the temperature of the chip, and as it travels, it goes through this contact of two different materials. So contact resistance right here. So when you're given this on the exam, the units for thermal contact resistance is meter square, Kelvin, or watt. And normally, any type of contact resistance is going to be in the units of Kelvin per watt. So we need to get rid of this meter square. So to get rid of that, we can multiply, or not multiply, but we can divide by area. And now it cancels out the meter square. So we have to divide by the area, and the area that this contact resistance acts is along the entire area right here for the length and width. So the next contact resistance, the heat is traveling through this solid material. So that's going to be conduction. And conduction is L over Ka, and this L is the Lb, which is the length of the base. And the area is also going to be the length times the width. And the next thermal contact, or the next thermal resistance, is going to be traveling through each of these fins. So thermal resistance for multiple fins is going to be 1 over efficiency of the overall fins, H, and the total area. And then we have our ambient temperature. So that's what the thermal resistance network will look like. Be sure that when you're writing these, write in the values of every single variable that you see, so you don't have to rewrite it through the entire problem. So for part B, you're going to be using your equation sheet. For adiabatic fins, which this problem is, we're going to use, for a single fin, the hyperbolic tangent, MLC over MLC. Okay. On your equation sheet, for a rectangular single fin, this is the efficiency equation you'll use, where the characteristic length is going to be the length of a fin plus thickness over 2, and m is going to be square root of 2h over kt, and you just substitute these variables in after putting in the actual numerical value for each variable. And that will be your answer for part B. And for part C, you're using an equation from your equation sheet once again, and that's 1 over number of fins times area of the fin divided by the total area times 1 minus efficiency of a single fin. So area of a fin, that's provided on your equation sheet, which is 2 times width times characteristic length, where characteristic length is, of course, from up here, so the LF plus T over 2. And then the total area of all, including every single fin, that's going to be number of fins times the area of fin plus the total area, so the length times the width, minus number of fins times the cross-section area of the fin. So this is going to simplify to number of fins times the area of fin, which is up here. You can rewrite it if you want, but I don't think you would have to, but I'll just rewrite it. Plus the length times width, and then minus the number of fins times the cross-section area of the fin. So you're using this area right here, so that's going to be the thickness times the width. Okay, so when you put all the numbers in for these, you don't have to put them back into here. You can just leave it like that, I'm pretty sure. So that will be part C. And now for part D, we're finding the heat rate. So from the thermal resistance network, we're doing heat rate equal to the difference in temperature divided by the total thermal resistance. So if we go from the known values of Tc and T infinity, we're going to be including all 3 thermal resistances. So we're going to have the Tc minus T infinity divided by the contact thermal resistance and dividing by area to put it in the correct units, plus the conduction thermal resistance, and then plus the thermal resistance of the total number of fins. Okay, and you don't have to rewrite this variable because you already listed it up here. And yeah, that is how you approach multiple fin problems. They're all relatively going to be the same. You just have to pay attention to the shape of these individual fins, the number of fins that you're provided, and yeah, I hope this video was helpful. Good luck to all of you.